All right, welcome to Lab 7. This is going to be a short little introduction video. I've already posted the video about the setup and data taking, but I want to just do a little introduction video to make sure everybody's on the same page, to make sure we all understand the analysis, and to let you know exactly what should be turned in for the informal report. So just quickly, let's take a look at this video in action, the pig moving. Here's a video of the pig in action. The pig is flying in a pretty stable circular path. What you want to get from this part of the video is two things. One, what is the radius of the circular path? Again, you're measuring that radius relative to the plumb. Okay, so that's basically what it looks like is you've got a pig connected to a string which is moving around in a circle. And since the pig is moving in a circular path, we know it's accelerating even if its speed isn't changing because its direction is changing. So if I look, here's a little picture of sort of the setup. We've got the flying pig, and I've got two different free body diagrams drawn. One of them would be what would happen in this case if the pig was right here. This is sort of the free body diagram that would be. And in the other case, this right here is kind of what would happen if we were looking at the free body diagram of the pig over here. Doesn't really matter, so let's just look at it in the case where the pig is to the left here. And so drawing a free body diagram, all we have are two forces acting on the pig. You've got tension in the rope, and you've got the force of gravity, mg. So one thing here that's useful is the way I have these angles defined. The angle here, theta, is the angle between the string and the vertical. So this angle here is theta, which means this angle here is also theta. So what I want to do is basically break up the tension into x and y components. So what I'm going to do is have a component of the tension, which is acting straight up, component of, well, gravity just acts straight down, and a component of the tension, which is acting to the right. Now, this right here is my adjacent side, and we know adjacent from SOH-CA is dealing with cosine. So this is t times the cosine of theta, and then t sine theta. So this is basically my free body diagram. And now all we're doing is applying the sum of the forces equals ma in both the x and y directions. So if I define my axes like x and y, then what I know is the sum of the forces in the y direction equals may, which in this case is going to be 0 because the pig is not moving up and down. It's just moving in a circle. It's not changing its elevation at all. And I know the sum of the forces in the x direction equals max, which in this case, the acceleration is centripetal acceleration v squared over r. So what you're going to end up with is two equations. One equation is going to have something like t sine theta equals something. Second equation, t cosine theta equals something. What you want to do is basically divide these two equations, and what you're going to get is an equation that has tangent of theta equals some quantity that's going to have v in it. And in fact, it's going to have v squared in it. So what you're going to end up with is solving an equation for v that basically you're going to have a square root of some stuff inside here. Inside here, basically, you're going to get just a function of r, g, and theta. So inside here, inside this speed v equals the square root of something, you're basically going to have a tangent of theta, you're going to have some function of r, and some function of g. Now what you want to do is you want to use trigonometry to convert tangent of theta into something that only depends upon r, the radius of the circular path, and L, the length of the string. So what you're going to do ultimately is get V as a function of just R, the radius of the circular path, L, the length of the string, and there'll also be G in here. So you're going to convert this function of tan theta into a function of L, the length of the string, and R, the radius of the circular path, just using trigonometry. So we're calling this V theoretical, is basically this square root of something that's going to be a fairly ugly expression. You're actually going to have a square root of a square root inside of here. This speed, this theoretical speed, is only going to be a function of R, L, and G. So the other thing is we're also going to get an experimental speed, which is just going to be 2 pi r divided by the period. So from the video, here's basically what you're getting from the video. You are getting r, the radius of the circular path, you're getting L, the length of the string, and you're getting the period t. You're only measuring 3 quantities. From those 3 quantities, you're going to get 2 things. One, let me change this to a different color. What you're going to get is an experimental speed from 2 pi r divided by the period. Second one, you're going to have a theoretical speed, which is going to be some function of r, L, and G. It'll be kind of an ugly function. You'll have a square root inside a square root, but fairly straightforward. And again, the way you get that is you're applying Newton's second law. Sum of the forces in the y direction equals MAY, which is 0. You're going to get one equation that's basically going to have t cosine in it. You're going to apply the sum of the forces in the x direction equals MAX, which is mv squared over r. You're going to get an equation with tension in it, or t sine theta. What you want to do is divide those 2 equations, get a function of tangent, which is going to depend on v squared along with some other quantities. You're going to solve for v. You're going to have basically an equation that's got just speed in terms of tangent, r and g. And then you're going to take this tangent theta and then replace it with some function of L and R. Just using tangent equals opposite over adjacent, but you don't want h here. You want to replace h in terms of L and G. Okay, so let me just erase this right here. Let me just tell you, in terms of the write-up, this is not going to be formal. This is going to be informal. And pretty much what I want to see for the informal report is pretty much just everything here, 1 through 6. So can we kind of go through it? What you're turning in for the formal report, and please make this nice and easy to follow, is draw a free body diagram of the forces acting on the pig. Pretty straightforward. I kind of did that for you. There's just tension and gravity. You're going to apply sum of the forces equals ma in both the x and y directions. So you're going to solve for the speed in terms of r, theta, and g. Then you're going to convert tangent theta into a function of r and L. I'd like to see how you actually do that conversion. Then ultimately, you're going to derive an equation for the theoretical speed that's going to be a function of r, L, and g. And that's kind of what I was doing over here. I didn't write the exact equation out because I want you to derive it. Well, this case, you're not going to set up the pig because basically you are watching a video. But what I want to see is what is the value of r that you get from the video, what is the value of L that you get from the video, and what is the period. You're not doing this multiple times. You're getting one value of r, one value of L, and one value of the period. Then your experimental speed will be 2 pi r divided by the period. Your theoretical speed will be the speed that you get by deriving an equation using Newton's second law. And then the last thing, the only analysis you're doing is you're giving me a percent difference. What is the difference between the experimental speed, which is our 2 pi r divided by the period, and our theoretical speed, which is going to be you deriving an equation, which is just in terms of r, L, and G. So that's it. I'm posting this video today. It's Monday. The data and setup is already posted. So this is the lab that you're doing this coming Wednesday, April 1st. All right, that is it. As always, I'm available by email. Let me know if you have any questions. I think this is a pretty straightforward lab, and it's a pretty popular lab. So if you needed to, you could Google search Flying Pig Lab, and there's lots of useful websites with information. But I feel like I've given you everything you need. All right, that is it. Tuning out for now.